Hi everyone, it's my great pleasure to come to visit KTH and present my work today, Human-Centered Geospatial AI, Understanding Human Experience at Place. I'm Yuhao Kang. I'm currently the director of GI Science Lab at the University of Texas at Austin. Today, I would like to present a series of work, including some of my key collaborators at KTH, including Professor Vania, Dr. Jonathan, Lucas, as well as Fabio at MIT. Before I delve into my research work, I would like to first introduce a little bit more about my past journey as a geographer and a GI scientist. I previously have been working at both academia and industry sectors, including University of Wisconsin-Madison, MIT Sensible City Lab, and Google X. I always define myself working at the intersection of these three research areas, including geography, computer science, and urban planning. In particularly, my past work primarily focused on the human dimensions of spatial data science. So what is spatial data science and what is human dimensions of spatial data science? So we are now living in the era of geospatial big data. Every second, every minute, people are generating huge volumes of geospatial big data, such as geotagged social media, like geotagged tweets, and all the vehicles and mobile phones are now equipped with GPS, which allow us to track mobility and human trajectories. We also have rich imagery data sources, such as remote sensing images and street view images, which allow us to characterizing the world with all of these useful and helpful data sources. To summarize, all of this geospatial big data provide new opportunities to help us better modeling and understanding and monitoring the environment. To handle such huge volumes of geospatial big data, we need some powerful tools. And as you know, in the recent years, the rapid development of AI, especially the Geospatial Artificial Intelligence, or what we so-called GeoAI algorithms, offers new opportunities. For instance, you may have tried ChatGPT. The AI can now even communicate with people. We also have some cutting-edge computer vision techniques which can help us to identify objects from street view images and even create some AI-based paintings. However, despite the emergence of these geospatial big data sets as well as advanced GeoAI algorithms, geographic phenomena are always treated as functions of a set of physical settings, while lacking consideration of the human subjective experience in the existing geospatial data science as well as AI research. But as human, a lot of seminal work in geography in urban planning have emphasized that people should be placed at the center of place. For instance, as Professor Yifu Tuan, who is a famous geographer, mentioned that people think that geography is about capitals, landforms, and so on. But it's also about place, its emotional tone, social meaning, and generative potential. So where is human? Where is a human? How can we enrich the current geospatial AI with our human experience? So, motivated by this question, my past work primarily focusing on the human dimensions of geospatial AI and geospatial data science. And I propose the human-centered geospatial AI focusing on two missions. One is to understand human subjective experiences, such as perceptions, emotions, cognition, personality, and creativity of human. For instance, when you go back to your home, so what's your perception of your home? Your home setting might be similar to your neighbor's home setting. However, what makes your home unique to you? What's your emotions attached to your home? what's your perceptions associated with your home? So these are human subjective experiences. How can we measure? How can we understand all of these subjective experiences which can advance our knowledge of human environment interactions? At the same time, despite that GeoAI algorithms are cutting edge and provide a lot of opportunities to address several real-world problems, it is still essential to develop responsible and ethical geoscience technology to ensure that GeoAI algorithms are utilized to prioritize human values in a responsible way to benefit the real-world applications. For example, GeoAI should mitigate bias, protect human geoprivacy, enhance explainability of GeoAI, as well as building inclusive GeoAI algorithms. So today, I would like to share a series of work primarily focusing on how can we leverage geospatial AI to understand human experience. Here is a brief recap of my past collaborative work with KTH. So in the previous studies, we proposed a computational workflow to measure human perceptions of the environment, such as whether a place makes you feel safe or not safe. Look at these two 3D images. These are two sample 3D images in Stockholm. And the hypothesis is participants' perceptions of 3D images are treated as a proxy of your perceptions of the built environment. Because 3D images can provide very detailed characterization of the built environment, and we can analyze the objects, we can analyze the scenes and the environment of the built environment. And after that, we can train an AI algorithm which can model human subjective experiences of the safety perceptions. So here, I would like to show you a few example samples predicted with our GeoAI algorithm. Look at these two sets of 3D images. Those on the top, those are images predicted with high safety scores, while at the bottom, those are 3D images predicted with relatively low safety scores. Luckily, this is a collaborative work between MIT and the City Planning Office in City of Stockholm, as well as KTH. After we train such a GeoAI algorithm to predict and to measure human subjective safety perceptions, we further create a map on the right side to show the spatial distributions of safety perceptions. So this work demonstrates how we can leverage GeoAI to understand human subjective experiences like safety perceptions. As safety perceptions, how you feel, how you perceive of the environment, subject to individual preferences. After we built this safety perception score, we further made some explanations to understand what contributes to safety perceptions. We identified several interesting findings, like high quality of the neighborhood's visual appearance and inner city views and prosperous economy are positively associated with human safety perceptions, while certain type of urban facilities, such as gas stations, might be negatively associated with human subjective safety perceptions. After we explaining these safety perceptions, we further make links to the crime, because we all know that what makes you feel safe or not safe of a specific place and neighborhood is usually associated with crime patterns, whether there are some crime. So we further examine the associations between such safety perception scores and crime, and we conclude that, generally speaking, places perceived as unsafe environments are associated with high crime rates, but different types of crime may have different impacts. After we examine the associations with crime patterns, we further examine the land use patterns to identify what are those environmental factors for safety perceptions. we delved into the 6 types of land use types in Stockholm, and we examined the safe places and unsafe places in all of these 6 types of land use. And we extracted what objects are dominant in those safe or unsafe places in different land use types. So all of this work have demonstrated that geospatial AI or human-centered geospatial AI offers promising opportunities to understanding human subjective experiences and places, and could inform urban planning, criminology, and geographic practices. So after this series of work, you might be curious about what's next. What's next? I was also thinking about, so what's next? I'm a GeoAI research scientist. I can develop cutting-edge algorithms, and I would like to embrace human-centered geospatial AI. However, although we measure and model the subjective experiences of place, can we encode more human experience, or can we leverage human behavioral knowledge into the GeoAI development? So in this case, I step back a little bit, and back to our human to think about how our human perceive the environment. So in the next few projects, I would like to demonstrate some of my recent work to leverage and develop human-centered geospatial AI to better understand human subjective experiences such as perceptions at place and even personality. So let's first think about how do humans perceive place. As you can see, in the previous work, we rely on 3-view images, and the hypothesis is our human perception of the built environment is treated as a proxy of the perceptions to the 3-view images, because 3-view images reflect our visual perceptions of the environment. However, at the same time, as human, we not only have eyes, we also have ears and like noises and the mouths and our hands we touch. It's not only one dimension of senses when we experience and interact with the environment. So is it possible that we can also integrate our acoustic or sounding environment into account? So the first project is to measuring multi-sensory place perceptions with generative AI. And the second one is to decoding place experiences with psychological methods. So let's move to the first project. And as a warm-up example, I would like to first play 2 audios. So when you listen to these 2 audios, I would encourage you to imagine where are those audios. You can make a guess what's the environment of those audios. The first audio is this. The second audio is this. So in the first audio, you might listening to some people are walking, and you can probably hear about the bird calls. Well, in the second audio, you probably can hear the traffic noise, right? And then you can make a match which audio is associated with which photo. So after you make the match, I feel the results should be very intuitive. But did you realize actually these images were not true images? They are actually synthetic images. In other words, they are actually generated by AI. So what motivates us is traditionally there is no effective way to visualize the auditory perceptions. As I presented before, we use our eyes, we rely on the visual perception to understand the human perceptions of the environment, but the auditory perceptions has been overlooked. This is because there are lacks of intuitive ways to effectively and vividly characterize the acoustic environment, especially when compared with those methods for visual perceptions. When you look at this image, this is an image for the audience in our UT football games. When you look at this image, you can imagine the sounding environment, right? You can imagine the noise environment. But how can we analyze the auditory perceptions? So far, it's restricted to spectrograms, acoustic signal attributes, but compared with its visual perceptions, like we can rely on image analysis, they are relatively not that intuitive. And also, as human, we experience the world with all senses simultaneously. But most of the existing studies have focused on a singular dimension of the human sense of place, while overlooking the complexity and the depth of human-environment interactions, which are inherently shaped by multisensory experiences. Have you been to some museum and joined some multisensory exhibitions? As human, we experience our world not only rely on eyes, but also rely on other dimensions of senses. The recent boom of generative AI offers new opportunities. And so far, there are two primary types of generative AI. One is the text-to-text models or the large language models, and the other one is text-to-image models. So those text-to-image models were, generally speaking, were developed based on diffusion models, such as Stable Diffusion, Midjourney, which can create graphics. And in computer science, there is actually a small domain called audio to image, which can translate auditory information into visual representations. And computer scientists have already developed some cutting-edge methods. However, all of those methods haven't account for geographic context. For instance, regarding the datasets, those models, prior studies rely on the general datasets, while overlook geographic and environmental settings. For instance, when a car's sound is presented, the model can generate a car. As geographers and urban planners, we are actually not curious much about the object itself, but we are curious about the environment, like what environment, shape, or causes those kind of sounds. So we hope that given an image, given a sound, we can show the environment of those sounds rather than the object itself. Also, prior audio-to-image models neither use DIT, which is a cutting-edge diffusion transformer, nor integrate geographic context. Finally, regarding the evaluation matrix, like how can we assess the images generated from the audio? Prior evaluation matrix may fall short in capturing geographic semantic alignment between the soundscape and images. For instance, here I presented some examples. From your eyes, you probably cannot differentiate their differences, but relying on some existing methods like FID, these images actually are different. As geographers and urban planners, what we are curious about is whether the environment generated are consistent between the input soundscape as well as the output image. So following all of these motivations and the challenges in previous study, we further provide a new problem. We frame this as a new problem called geocontextual soundscape to landscape problem, and we propose a cutting-edge SounDiT model to support this geocontextual soundscape to landscape problem, which is to generate landscape images from environmental soundscapes guided by an optional scene prompt. So if we do so, we ask the question, can we visualize what we hear? And our SounDiT model has the potential to visualize the environment of the input soundscape. And luckily, our paper and our projects were recently published and reported by a few national level TV channels. So to support this problem, we first create two large-scale datasets, including SounDiT SVI and Sonic Urban. So these two datasets provide large volumes and high diversity of soundscape and images around the world. So to generate SounDiT SVI, this dataset, we first retrieved geotagged soundscapes from an openly available platform, Apori. Because all of the soundscapes are associated with a geotag, we then retrieved its nearby 3-view images to generate the sound image pairs. We also create another Sonic Urban dataset. To create this one, we retrieved several YouTube videos based on keyword search, such as New York City walk, etc. Because videos itself contain both images and sounds, so we also create another set of sound image pairs. So on the right, you can see several images in our Sonic Urban. After that, we further propose SounDiT, which is an advanced diffusion transformer-based model. We develop a new SounDiT block, which can successfully integrate both soundscape as well as landscape embeddings into this model. And we further provide a scene prompt, which allows flexible inputs such as text like streets, forest, beach, to ensure the control of different inputs. And as previously mentioned, we also need some geocontextual evaluation framework. Following several urban planning practices, we propose a practice-informed evaluation framework called Place Similarity Score. Because the hypothesis is soundscapes of landscapes are expected to share similar environmental characteristics and place settings. So we further assess the place similarities or the environmental characteristics across 3 levels, including urban elements like trees, buildings, road, urban scenes, such as the categories like natural environment, park, beach, urban environment, etc., as well as human perception levels, such as our safety perceptions, which can assess whether the soundscape, the input soundscape, and the output landscape demonstrate similar environmental characteristics. So here are a few examples with high PSS place similarity scores at the 3 levels, at the element level, at the scene level, as well as human perception level. So as you can see, the ground truth and the AI-generated images, generally speaking, are similar regarding the place settings. We further compared our results with a few other baseline models. And as you can see in the last 2 columns, our SounDiT, the generated images, look similar to the ground truth regarding its environmental and place characteristics. We further presented a few quantitative metrics to compare with other baseline models, including both general metrics as well as our place similarity scores. Our model outperforms other baselines in most of the metrics. Furthermore, to validate and to assess the performance of our SounDiT model, we also conducted a user study to ask people whether the SounDiT can generate the realistic images, similar to the examples I demonstrated with you at the beginning. Like we presented a few images and asked people to rate like which one is associated with the input soundscape. So to summarize, in this work, we propose a novel SounDiT model that translates soundscapes into 3D images. We step back from the perceptions and think about how humans perceive the environment. We not only rely on our eyes, we not only rely on our visual perceptions, but we also rely on our ears to understand the soundscape, to understand the acoustic perceptions. And understanding multiple dimensions of sense of place by combining human auditory and visual interactions with the environment to enrich our understanding of the environment by enriching a new dimensions with a cutting-edge SounDiT GeoAI algorithm. And we believe that this model may benefit human mental health and may further inform urban design. So that's my first project. We measured multisensory place perceptions with generative AI, moving beyond the visual perceptions, but we also account for sounding environment. The second project, similarly, we decode place experiences with psychological methods. The reason, the motivation is that can we really trust the GeoAI generated outcomes? Are they truly reflect human behaviors? So in this case, it's still necessary to include and integrate human behavioral datasets to better understand the GeoAI algorithms. So here is a recap of our previous paper measuring safety perceptions. As you can see, we leverage GeoAI algorithms predict 3D images to generate the high safety scores or low safety scores. And further, we create a map on the right to show the spatial distributions. And how can we understand what environmental objects contribute to safety perceptions? Traditionally, assume this is an input 3D image. We can then run the semantic segmentation to identify different objects and elements in built environment. After that, we can calculate the proportions of objects and then link with safety perceptions. After that, we can then examine the associations by calculating the correlations or run some regression methods to build the models to understand how the proportions of objects associated with human safety perceptions. So that's a common practice in several similar studies. At the same time, some of the AI research scientists, they have developed what we so-called the explainable AI or XAI methods. And some researchers have explored the usage of XAI methods to understand what environmental objects contribute to our safety perceptions. For instance, GradCam is one of the most popular methods that have been leveraged. These XAI methods to understand what pixels are important in influencing the AI outcomes. Like this one, this group of researchers leveraged GradCam and generate some heat maps and then associate with safety perceptions. So their conclusions are those regions highlighted play a more important role in influencing the GeoAI-based safety perceptions. Here comes to the question, are these explainable AI methods truly reflect human behaviors? Can we really understand and trust the outcomes generated by these XAI methods? So in another following work, we decode the safety perceptions with eye tracking systems in Hessenberg to capture participants' focus when looking at 3D images. Because eye tracking systems can precisely track where and how long individuals focus their gaze when viewing images or environment. Collaborating with some of my exceptional collaborators in Sweden, so we deployed the eye tracking systems in Helsingborg, Sweden. And after that, based on the eye tracking systems, we generate a few heat maps to understand human behavioral patterns when judging safety perceptions. So as you can see, assume we have the original image. After that, we can run AI-based semantic segmentation to identify different objects. Based on the eye tracking systems, we can also generate a heat map, which reflects how people perceive the environment. We further leverage the several explainable AI algorithms, all based on cams, such as GradCam, XGradCam, EigenCam, etc., and also generate some heat maps. So we further can assess whether the explainable AI-based heat maps are similar to the eye tracking-based heat maps. So here are a few sample street view images as well as the attention heat maps. So look at this. We identify the highlighted regions of each street view images for both images classified as safe and classified as unsafe. We further identified what environmental features do individuals mostly focus on when they viewing those street view images. And we identified that signboards, cars, trucks, and plants are more significant and attract human attention in images predicted with safe. While trucks, vans, cars, houses, doors, and plants are more significant in those images predicted as unsafe. One interesting finding is that the eye tracking data showed that the sky and pathways, such as paths and sidewalks, were perceived as less significant. This is an interesting finding because in a lot of prior studies, sky always occupy a large proportion of images. But if we leverage the eye tracking data to understand how people perceive the environment, actually sky is not that important in attracting human perceptions, which informs the future potential applications. For instance, whether we should still account for sky or related like openness design. So this work using eye tracking systems, we first understand what environmental features do individuals mostly focus on when viewing street view images to make a judgment on safety perceptions. And if you recall, I presented a few explainable AI methods. We want to examine can gaze heat maps validate the outputs of the XAI methods. So we indeed identify several mismatches. We compare the AI generated heat maps as well as human gaze heat maps using eye tracking, and we compare them. So we compare their similarity, and we notice that among all the methods we tested, XGradCam and EigenCam may offer greater reliability and might be more trustworthy when using XAI methods for future perception-related applications. So to summarize, I'm currently working on the human-centered geospatial AI to understand human experiences such as human perceptions. In my previous work, collaborating with KTH, we developed a GeoAI-based algorithms which can modeling and measure human subjective safety perceptions of the environment. After that, my work stepped back to think about how our human really perceive the environment. And we focus on two perspectives. One is that we should integrate acoustic or sounding environment into the perceptions rather than relying only on the visual perceptions. And the second one is that we should also integrate human behavioral data to better modeling the human perceptions. We leverage eye trackings to understand how people, what environmental features attract the human perceptions, and also compared with XAI methods to find whether the two methods, whether the human-based methods and XAI-based methods align with each other. So that's most of my previous work, and as I briefly mentioned that we are measuring multiple dimensions of human experience, not only the perceptions, but also emotions, cognitions, personality, and creativity. So one ongoing project that we are working on is that we examine the human personality traits and the built environment. So here is a paper that is currently in revision in the Annals of AEG. We collaborated with psychologists who have over 10 million of human personality traits data around the world, and we're focused on 4 cities in the United States, in the Texas, including Austin. We built a computational workflow to measure what environmental objects extracted from trivial images and how are they associated with human personality. Because people are always curious about whether your personality traits is determined to what degree it's determined by the built environment. So we examined their associations and we identified several interesting findings. For example, one interesting finding is that number of American flags are negatively associated with openness and agreeableness. So this is a new direction to understand human-environment interactions. By working with psychologists, we can integrate more psychological methods such as those eye tracking or other neurosensing methods, as well as those psychological survey into studies to examine their associations with the built environment and with geography and also urban planning practices. So to summarize, as you can see, cutting-edge GeoAI methods provide novel opportunities to advance the knowledge of human experience at place. Traditionally, human subjective experiences are challenging to be measured, to be collected. But now, with GeoAI, it's possible that we can measure such subjective dimensions of human experience. At the same time, geographic principles as well as theories are still essential in enriching the current geospatial AI and the geospatial data science, such as those subjective experiences or human behaviors patterns are still necessary to enrich the GeoAI, and it's necessary to have human in the loop to validate the results of GeoAI-based outcomes. Finally, more psychological and neuroscience datasets and methods might be integrated to better examine human-environmental relationships. As you can see, by leveraging eye tracking, neuroscience technologies, as well as psychological metrics, we can advance our knowledge of the human-environment relationships. Okay, I think that's all for my presentation. It's really my great pleasure to come and visit KTH. An interesting story is that although Stockholm was my empirical settings in my previous study, but it's actually my first time to come and visit here to tour around this to understand which regions make me feel safe or not safe. And all of this work cannot be accomplished because of my key collaborators such as Professor Vania, Jonathan, Lucas, as well as those people working at MIT Sensible City Lab. Okay, I think that's all for my presentation. Thank you.